In the last lesson, we learned how to solve for the mixed strategy Nash equilibrium in something known as the matching pennies game depicted here. At the end of the lesson, I noted that the mixed strategy Nash equilibrium is at least a little bit weird. Remember, the definition of a pure strategy Nash equilibrium is one in which no player has an incentive to change their action. That condition is actually true as well in a mixed strategy Nash equilibrium. However, there's a funny implication when considering mixed strategy Nash equilibrium. And I mentioned this in the last lesson. It's that for a player to be willing to randomize, that player must be indifferent among all of the actions that it randomizes among. So what do I mean here? Let's go through an example with some math and kind of explore this idea a little bit more. So remember, the Nash equilibrium, or the mixed strategy Nash equilibrium, is when both players randomize with probability equals 0.5. They play heads with probability 0.5, and each of them plays tails with probability 0.5. Okay, so let's look at player 2's expected utility when player 1 randomizes with probability 0.5 and player 2 plays heads. Well, in this case, 50% of the time, player 1 will play heads, and because player 2's strategy is fixed at heads, they'll match, so player 2 will earn 1. But 50% of the time, player 1 will play tails. Because player 2's strategy is fixed at heads, they won't match, so he'll get a reward or a utility or a payoff of -1. And of course, in expectation, the average payoff for player 2 is 0. How about the expected utility for player 2 when player 1 randomizes with probability 0.5 and player 2 plays tails? Okay, again, this is relatively straightforward. 50% of the time, player 1 will play tails, so player 2 will earn a payoff of 1. But 50% of the time, player 1 will play heads, and because player 2's strategy is fixed at tails, he'll get -1. And of course, this is equal to 0. Now, what is player 2's? So first of all, we see that player 2, when player 1 is playing 0.5, which is the mixed strategy Nash equilibrium, he's indifferent between playing heads and tails. And you can do the math out, but if P was greater than 0.5, then expected utility for player 2 would be greater by also playing heads. And if P was less than 0.5, player 2's expected utility would be greater when he plays tails. But assuming player 1 is randomizing with probability 0.5, what is player 2's expected utility when player 1 randomizes with probability 0.5, but player 2 randomizes or plays heads with probability Q? Okay, we can write this out. So it's 0.5 times Q. This is them both playing heads. So 0.5 times Q proportion of the time, player 2 will earn 1, plus 0.5 times 1 minus Q. This is player 1 playing tails and player 2 playing tails, because 1 minus Q percent of the time, player 2 will play tails. He'll get 1. We can keep going here. So half the time, player 1 will play heads and player 2 will play tails. This is equal to and he'll get a payoff of -1. And half of the time, player 1 will play heads and player 2 will play tails. And he'll get -1. Oh, actually, sorry. Player 2 playing tails is actually 1 minus Q, because remember we said he plays heads with probability P. So this is 0.5 times 1 minus Q. And in this case, they're mismatching. Player 1 is playing heads, player 2 is playing tails, so player 2 gets -1. If we multiply this out, this is just a simple equation, we see that independent of Q, player 2 will earn 0. So what does this mean? When player 1 randomizes with probability 0.5. Player 2 is indifferent between always playing heads, always playing tails, or randomizing between heads and tails with any probability. So, what probability does the Nash equilibrium, or the mixed strategy Nash equilibrium, assign to Q? Well, the mixed strategy Nash equilibrium says Q equals 0.5, because if Q is equal to 0.5, then player 1 is indifferent between playing heads, playing tails, or randomizing with any probability, including probability 0.5. So, if both players are playing heads with probability of 0.5, no player can do better by changing its strategy, but the players are indifferent among any of the strategies they can choose, as well as any probability distribution they place on their actions. So, like I said, the mixed strategy Nash equilibrium is a little bit weird because in equilibrium, although the players are what we call best responding, they can't change their action to do better. They are indifferent. They don't care which action they choose because all of their actions that they randomize among gives them the same payoff. Now, this is really digging down into the weeds of a mixed strategy Nash equilibrium. And as I said in the last lesson, this is kind of a bonus for those really interested in mixed strategy Nash equilibrium and looking to go on further their studies in game theory. If this is unclear, no worries. The rest of the lessons will focus on pure strategy Nash equilibrium. Like I said, this is a bonus lesson, and I will provide some extra references for those interested in learning more.